So let's welcome third lecture of MAT-601. So this is our third lecture. So last lecture, that is second lecture. So I have taken on 4th June 21. So this is our lecture number 3. Just a minute. So in last lecture, so we have started second chapter, that is continuous functions on matrix spaces. So in this chapter, so there are 3 points. For first point, that is 2.1, functions continuous on matrix spaces. 2.2, that is open sets, and 2.3, that is closed sets. It is a very short chapter. So functions continuous on matrix spaces. So in that, first we define open ball. It is also called open sphere. So just revise what we have seen in last lecture. Let's see. So first of all, we have seen definition of open ball. So what is the definition of open ball? So let's suppose M row be a matrix space, and if A is any element of capital M and R is any real number, so which is positive real number, then so BAR, open ball about A with radius R, is defined to be the set of all points in M whose distance to A is less than R. That is, so in set notation we can write it as, so what is capital BAR? Open ball about A with radius. You can read it as open ball at A with radius R. So it contains all x belongs to M such that rho of x is strictly less than R. So it contains those points x whose distance from A is strictly less than R. So R is positive real number. This is definition of open ball. It is also called open sphere. So we call BAR the open ball of radius R about A. So geometrically, so you can see, suppose capital M is a metric space and put this open ball about A with radius R. See, so center is A, center of this ball is A and its radius is R, means so this distance is R. So what is this set BAR? It contains those points. See, what is problem? It contains those points whose distance from A is strictly less than R. So all these points. So you can see all these points will be in open ball. It contains all these points of matrix space M. So this is geometrical representation of BR. Also, so if suppose Y is element of BR, then what you can say about this Y? So distance of A and Y should be strictly less than R. So this condition for Y belongs to BR. So in latter part we'll use this logic. This problem. Just need. Is not working. Yeah. Yes. So after that, we have seen definition of continuous function at a point. The function f is continuous at a belongs to capital M1. So f is a mapping from. So obviously, so this condition is there. So f is a mapping from capital M1 to capital M2. So it is there. So f is mapping from matrix space M1 to matrix space M2. So small a is element of capital M1. So M1 is matrix space. So when we say f is continuous at point A, so if limit of fx as x tends to a should be equal to f of a. So this is basic definition of continuous function at a point. So we take next theorem. We stated already this theorem and we state it without proof. So this theorem provides alternate definitions of continuous function at a point. So this theorem contains three definitions of continuity at a point. The function f is continuous at a belongs to m1 if and only if n1 and hence all of the following conditions hold. So first condition is that given epsilon strictly greater than 0, there exists delta greater than 0 such that rho 2 of fx fa is strictly less than epsilon whenever. So rho 1 of xa should be strictly less than delta. So this is a limit form definition of continuity. Just we write it in epsilon delta form. What is second statement? The inverse image under f of any open ball about fa with radius epsilon about fa contains an open ball about a with radius delta means every open ball inverse image of every open ball about fa with radius epsilon contains open ball about a with radius delta. So this is second definition of continuity. You can call it as open ball form of definition of continuity. And what is third? Whenever xn is a sequence of points in M1, so converging to A, then the sequence f of xn, that is sequence of image point of points of xn, should converge to f of A. So this definition is called sequential form of definition of continuity. So the previous theorem provides alternate definitions of continuity at a point. So up till this we have seen in last lecture. So let us continue. So there is next theorem. So statement of theorem is that, so let's suppose there are three matrix spaces. First matrix space, that is M1 row 1, M2 row 2, and M3 row 3. Be three matrix spaces, and let's suppose F is a mapping from M1 to M2, and G is mapping from M2 to M3. So if F is continuous at A belongs to M1, so small a is element of capital M1, and G is continuous at Fa of M2. Then G of F, that is composition of G and F, is continuous at A. So composite mapping should be also continuous. So in short, you can write this theorem states the continuity of composite mapping. So you can write here, yeah, continuity of composite mapping. If F is continuous at A, G is continuous at Fa, then F of G, sorry, G of F, so which is mapping from capital M1 to M3, and this mapping should be continuous at A. C. So F is continuous at A, G is continuous at Fa. So F is element of M2. Then composite mapping G of F, which is from M1 to M3. So it also continuous at A. So already we have seen proof of this theorem in continuity, that is MAT-601 in differential calculus. Very simple. So we'll skip it. So next theorem, let M be a matrix space and let F and G are continuous real valued functions at A belongs to M. So this theorem states operations on continuous functions. So you can add, subtract, and multiply continuous functions. Its continuity remains constant. So preserves, we can say. So let M be a matrix space and F and G are continuous real valued functions at A belongs to M. Then F plus G f minus g and f into g are continuous at A. Furthermore, if j is not equal to 0, then f upon g is also continuous at A. So all these theorems already we have seen in real numbers. So we can extend these theorems in matrix spaces. Proofs are straightforward, obvious, already we have seen. So next definition, that is definition of continuity on a matrix space. So let M1 and M2 are two matrix spaces, and suppose F is a mapping from M1 to M2. So we say that F is continuous function from capital M1 into M2 if F is continuous at each point in M1. If that mapping is continuous at each point of that matrix space M1, so we can say F is continuous on M1. So this definition is nothing but continuity, continuity on matrix space. If mapping is continuous at each point of M1, so we can say F is continuous on M1. So next, so let's consider one example. So example is that show that every function from Rd. So what is Rd? It is a discrete matrix space. So already we have seen. So every function from Rd into any matrix space is continuous on Rd. Means if F is mapping from Rd to any matrix space M, then that mapping is always continuous. Whatever, so it's a domain set, so it does not matter. So let F be a mapping from Rd to M be any matrix space. So it can be observed that for any A belongs to Rd, so if you take any element of Rd, so the open ball about A. So if in particular, if you take epsilon equal to 1, then what happens? So open ball about A with radius 1 contains only one point, because what is the definition of open ball? C. So what is B? A1. It contains all x belongs to Rd such that so distance of x and A should be strict less than 1. But in Rd, what is the definition of dxa? So distance between x and A is either 1 or 0. If x is not equal to A, then distance is 1, and if x equal to A, then distance is 0. If x is if distance is less than 1, so what it means that, so this distance should be 0. Means, so in that case, if dx is less than 1, so it obviously it implies that, so if distance is less than 1, then it should be 0. So in that case, distance will be 0. Means open ball about A with radius 1 contains exactly one point. So in that case, you'll write, so instead of this, you'll write x is equal to A, because it is true only when distance between x and A equal to 0, and distance between x and A equal to 0 if x equal to A. So that will imply, so open ball about A with radius 1 contains only one point, and that is A. So this for any epsilon greater than 0, the inverse image under F of open ball about FA with epsilon, radius epsilon, certainly contains open ball about A with radius 1, because this open ball contains exactly one point, and that one point always, so whatever that radius you take, so that open ball contains its center. So naturally, so inverse image of this open ball, it will be again open ball about center A, and its radius may be different, but surely that open ball contains that point A, because this open ball exactly contains single point. So this shows that F is continuous at A. Since A was an arbitrary point in Rd, so we have this solution. Means, so what this problem states that, this problem states that if F is any mapping from discrete matrix space, that is Rd, to any matrix space, then that mapping is always continuous mapping. That is, every mapping on discrete matrix space is always continuous mapping. So there is some homework. So you can do it at home. Hope you are doing previous homework also. So you can do it at home. So give an example of function which is continuous on R1. So what is R1? It is absolute metric space and whose range is this. So you should define a mapping from R1 and whose range is this. So for example, if you consider A, means you have to define a mapping from R1 to open interval 0 infinity, and that mapping should be continuous mapping. It means that, so you can define fx equal to suppose x square for all x belongs to R1. So naturally this mapping satisfies this condition because it is polynomial mapping which is continuous everywhere. So naturally it will be continuous on so set of real numbers. So yeah, so this mapping will be continuous on R1 and its range is set of positive real numbers. So obviously it is set of positive real numbers. So similarly you can define remaining. So you can do it at home. So what is second question? Second question is that, so let f is a mapping from R square to R, be the function from R square onto R1. So what is R square? Euclidean 2 space. Already we have defined Euclidean n space, and R means R1. So naturally, so that will be R1 with the mapping from R square onto R1 defined by, so this mapping is defined by f of order where xy is equal to x. So both this x and y are elements of R. So f image of order pair xy is equal to x means first component of this order pair. So for all xy belongs to R square, question is that show that f is continuous on R square. So just you have to use sequential definition of continuity. So here I can write hint, use sequential definition of continuity. So here already and third question. Yes, if f is a mapping from R square to R square and it's defined by f of xy equal to yx. Again, you can use here sequential definition of continuity. If f of xy equal to, so order pair xy. So what is the image of order pair xy under f? So it is order pair yx. For all xy belongs to R square, question is that show that f is continuous on R square. So simply use definition of continuity, that is sequential definition. Means if, see, xn is a sequence which converges to x, yn is a sequence which converges to y. So it implies that or sequence order pair xn yn converges to order pair xy naturally. And what it implies? It implies that it means that it implies that, see, what is f of xn yn converges to, so naturally it will converges to f of xy, and if f of xn yn converges to f of xy implies that f of yn xn it converges to f of yx naturally, and it will implies the continuity of this function. Very simple, just you have to use sequential definition of continuity. So next we'll start 2.2, that is open sets. So first we'll define definition of open set. Yeah. So this definition of open set. This problem. open set. So let M be a matrix space. So we say that the subset G of M is an open subset of M, or more simply that G is open. See, so M be any matrix space and G is any subset of M. So when we say G is open in M, if for every x belongs to G, there exists a number r strictly greater than 0 such that the entire open ball about point x with radius r should strictly lies in G. Means it is contained in G. Suppose, so you can observe here, see, suppose just it's okay. Suppose it is matrix space M, and so G is a subset of M. So if you take suppose X, which is any element of G, so when we say G is open in M, if you take any element of G, means any point of G, there should exist always positive real number such that, so by taking that positive real number, you should draw open ball about that point. So what is R? R is strictly than 1. It should be strictly than 1. So it is just positive. You can take very small value of R or very large value of R, that depends on that point, whether it is near to boundary point or it is middle of G. Means what is open set? It does not contains boundary points. Means if X is here, just this problem. Yeah. Means if X is on boundary, then what happens? You cannot find such a real number. By taking that real number, you cannot draw open ball. So if you draw open ball by taking very small radius, half part of that open ball will lie outside of G. So this is not true. So when we say G is open, see, for every x belongs to G, there exists a number r is greater than 0 such that the entire open ball about point x with radius r should contain in G. Means whole that open ball should lie in G. If suppose that point is here, you can take that real number very small, and by taking that small real number, you can draw open ball about x, which will totally contain in G. So it will totally lie in G. So which points will be there in G, or how G looks like? So you can imagine. So these boundary points will surely not lie in G if G is open. So this is basic definition of open set. So I will repeat once again. So let M be a matrix space. We say that the subset G of M is an open subset of M if for every, it is very important. So for every x belongs to G. So you should find such real number for every point of G, whatever that point. So it is interior points or whatever. So you can imagine if it's totally line G, then surely we can find such a real number, but if that point lies on boundary, then it is not possible. It means that if G is open, then it does not contain its boundary. So these boundary points are not there. If G is open, so you have to remove this boundary from G, and it will just contains interior points of boundary. See, so that entire open ball should contain in G. So there is one example, and this example is very important. So I will solve this problem. So example is that show that for any arbitrary metric space M rho, any open ball. So you can take any open ball, that is open ball about A with radius S, is itself an open set. Means every open ball is always open set. Itself is open set. This will justify the use of the word open in open ball. So why we are using this word open in open ball? Why I'm not just using ball or sphere? I'm using open ball. So what is significance of this word open? Because itself this set is open set. See, so we'll solve this actually. Yeah. So let suppose BAS, that is open ball about A with radius S, is any open ball in metric space, suppose M. So naturally rho is a metric for M. So our claim is that we have to prove that this open ball is open set. So naturally, what is the definition of open set? So if you take any element of this open set, sorry, this set, then there should exist a natural number r greater than 0, such that the entire open ball about x with radius r should strictly contain in G. See, so if x is any element of this open ball about a with radius S, I'm taking arbitrary point from open ball A with radius S. So we must find radius r greater than 0 such that so open ball about x with radius r entirely containing this open ball A with radius S. So that will imply this open ball will be open set. So this will be, yeah, our requirement. If x is any element of this open ball, so there should exist positive real number. By taking that positive real number, if you draw open ball about x with radius r, then that open ball should contain this open ball about a with radius s. So for that, so you can draw so figure. Suppose this is our original open ball, that is open ball about a with radius s. So this original open ball, which we have to prove it is open set, and we are taking any general element, general point, that is x, from this open ball. So we are taking x as a general or arbitrary point of open ball with radius a with radius s and center a. So let us take t. So I'm taking here t. What is t? See, t means you can see this blue distance, that is distance from a to x, and r be any positive real number, and which is strictly less than s minus t. So what is s minus t? You can see this black distance means this to this. This is s minus t. This is t. So what is r? R is strictly less than s minus t. I am picking real number r says that its value will be strictly less than s minus t. So you can observe that. So s minus t is greater than equal to 0. So basically s minus t is greater than equal to 0. If s minus t equal to 0, then what happens? Then s and t will be same. It means that so this point x will be here. So if s minus t equal to 0, then what happens? See, so s and t will be same, and in that case this point x will lie on this boundary point. So this is not true, sorry. So naturally s minus t should be strictly greater than 0, not greater than equal to 0. See, so if y is the point, if y is any point of this open ball about x with radius r, so I'm picking r. How I'm picking r? R is greater than s minus t. So by taking this radius r, I'm drawing open ball about x with radius r. So this open ball may be like this. You can observe. See, so I'm taking radius r and center x. So if y is any element of this open ball about x with radius r, then what happens? So distance between x and y should be greater than r. So naturally, so rho xy should be strictly less than r. Also, so distance between a and y, I'm using here triangle inequality. So what is distance from a to y? So what is y? So y is any point of this open ball about x with radius r. So it may be here or somewhere. See, so what is distance from A to Y? So I'm using here triangle inequality. So using triangle inequality, this distance will be less than equal to, so row ax plus row xy. So simply I'm adding here single point x. So this is triangle inequality, which is nothing but just triangle inequality. Since, so next, so distance from A to x is t. So already we define it. So distance from A to x is t. So it is here. And so distance between x and y is less than r. So naturally, so what is distance between x and y? So x and y is less than r because y is point of open ball about x with radius r. So naturally from here, see, and here, see, so you'll find, so since distance between a and x is t and distance between x and y is less than r, so I'm putting these values here in triangle inequality, so which I have written. So therefore, what is distance from a to y? So I'm putting this as a t and I'm putting greater value than this. So this quantity will be greater than, so plus r. But what is r? So already we have picked r such that its value is less than s minus t. So again I'm putting greater value than r. So that will imply, see, yeah. So it will be less than t plus r, but r is less than s minus t. So this t and minus t will be cancelled and that will imply, so distance between a and y is less than s. Hence, so what it imply? It will imply, so y will be element of open ball about a with radius s because distance between a and y is less than s. Already, what is y? So already we have taken, see, already y is element of row, sorry, y is element of open ball about x with radius r. See, so we figured y from this open ball and we proved it is also element of this open ball, that is open ball about a with radius yes. Means this open ball will be subset of this open ball. So it proves that open ball about x with radius r containing open ball about a with radius yes. So what is x? X is any element of this open ball. So that was our initial assumption. See, x is general element of this open ball about a with radius yes. So naturally that will imply, if x is, this problem, just a minute, yeah, if y is any element of open ball about x with radius r, then it is also element of open ball about a with radius yes. So it implies that this open ball about x with radius r totally containing open ball about a with radius yes. It means that if x is an element of open ball about a with radius yes, then there exists real number r. Says that by taking this real number, if we draw open ball about x, then resulting open ball is totally containing this original open ball. So that will imply open ball about a with radius is open set in M. So this is solution of this problem. So we'll stop here. So if you have any problem or query, so you can unmute yourself and you can ask directly. I think there is some problem for this OneNote app. So it is not working properly. If you have any query, you can ask. So I will stop here. Is there any problem? तुम्हाला काही प्रॉब्लेम आहे का? Yes. Okay. So I'll stop here.
पूजा
काय
तरी प्रॉब्लेम आहे का?
प्रॉब्लेमच प्रॉब्लेम.
समजतंय का आता?
नाही. काय करते मग?
होईल.
काय माहिती.
यार टेन्शन येऊ राहिला आता लय हा.
हा ना. मला फक्त डोके सरच आणि काकडे सरच समजत, बाकी कोणाचंच नाही. कम्प्युटरच अजून काहीच नाही म्हणून ते तर डोक्याचच भारी.
मला पण डोके सरच समजतं, काकडे सरच मी लेक्चर करते मधून जाते काही त्याच्यामुळे थोडं थोडं समजतं थोडं थोडं.
कसा वाटला? माझी स्लीव झाली होती.
पप्पा आलते ना.
अच्छा.
काय करता बाई
सरच
माहित
लेक्चर आहे आता
लेक्चरच व्हाय
डोक्यात.
नाही.
हा
12:30
माझ्यापेक्षा जास्तच करते.
हा
गोडसे सरचे माझ्या याच्या आधीच लेक्चर पण नाही केले. बघावं लागते.
पण मग सरांनी रेकॉर्डेड लेक्चर पाठवलेले आहे ना.
हा ना मग तेच बघावं लागते.
तरी नाही समजत बाई, मी 2दा उचकून बघितली.
हार्ड आहे काय समजत नाही मला पण.
नाही ते मागच्या सेमिस्टर मध्ये झालेलं नाही ना, सर बोलले फोनवर. मागच्या सेमिस्टर मध्ये एवढं क्लिअर झालेलं नाही म्हणून यावेळेस थोडं हार्ड जाईल म्हणे. पण तुम्ही तुमचा सेल्फ स्टडी ठेवा जा म्हणे. म्हणलं हा सर. सेल्फ स्टडी नावानं काय दम वाढेल आपल्याला.
मला मागच्या सेमच कळलं नव्हतं, या सेमच काय कळलं.
तेच ना मागच्या सेमचं मला कुठं कळलं. मी म्हणत होते सर डीपली घ्या. एवढा टाइम आहे का, तुम्ही काय करा ते करा. काय गेलं मागचे सर. एक फॉर्म पण आले.
फीस किती आहे आपली?
मोहित बोलला की
एक्झाम
1000 कितीतरी आहे.
एवढी?
हा ना बघ ना, BA ची तर
आपल्याला दिलंय
650 रुपये.
आपल्याला अजून ही पण भरायची आहे
फी
ऍडमिशन.
ना माझी मम्मी कालच म्हणत
4,775.
होती.
काय?
लय फी लागेल म्हणे यावेळेस, म्हणलं हा.
कांदे भरायचे सुरू करा मग आता. कांदे.
तुमच्याकडे
कांदे
हाय
काय
कांदे,
बाहेरचे?
आमच्याकडे कायचा पत्ता नाही.
नको फेकू.
खरंच ना.
जाय. काय केली मग कांदे तेव्हाच विकले काय?
कायची विकली सडून गेले तर. अख्ख्या वावरामध्ये कांदे कांदे फेकून दिले आम्ही 1.5-2 ट्रॅक्टर. आणि काही भरले ते पण काय भाव नव्हता ना तेव्हा माझं. गेले 550 रुपये का काय.
किती?
550.
बाबो.
आमचा तर खर्च पण नाही निघला, इतके तोट्यात येईल आम्ही या वर्षी. काय कामाचं एवढं शेत असून मला काही होत नाही बाई.
जाऊदे.
आता फिचले टेन्शन आहे पाहावं लागेल काहीतरी करायला लागणार.
बस झालं गप्पा चला.
आता लेक्चर आहे लगेच डोके सरच लिंक आलेली.
हा
चलो चलो जल्दी चला.
दोघे गप्पा करू राहिले ग कांदे बटाटे.
बरं झालं तू नको आता मध्ये चालली त्याला डोकेस तिकडे वाट
मी
बघत असते.
चला मग लवकर.
काय म्हणते भारती?
भारती बिझी पर्सन आहे. गेली बाय
ए
काम
गेले
करते.
सगळे चल गौरी.
हा